In this video, I've put some practice questions on IAL Edexcel Chemistry Unit 1 with answers and detailed explanations. The first 6 ionization energies of an element in kilojoules per mole are shown. Which group of the periodic table includes this element? Now, how do we determine the group from ionization energies? So the first thing we do is to understand what ionization energy means. So when we say ionization energy, or IE, this is the energy used to remove the electrons. So when we say first ionization energy, this is the energy to remove the first electron. And then second ionization energy, this is the energy to remove the second electron, and so on. And as you remove more electrons, ionization energy increases steadily until you try to remove a core electron. Then there is a big jump. So, big jump. So we look for the big jump in values. That means a big shift of values. So in this problem, we're given here 6 ionization energies. We have the first one, the second one, third, fourth, fifth, and the sixth. So let's take a look at the values here. Notice that between the third and the fourth ionization energies, there is a huge difference, or a huge jump, or what we call big jump between these two values. So why is there a very large jump? A very large jump happens once all the valence electrons are gone and you start pulling from the inner shell. So what we do first is we look for the big jump in the values. Once we already identified the big jump in the values, which in this case between the third and the fourth ionization energies, we now count the number of electrons before the big jump. So the big jump occurs on the fourth ionization energy. So we count the number of electrons before the big jump. So we have 1, 2, 3. So we have 3 electrons here before the big jump. And this number, okay, that number of electrons is just equal to the number of valence electrons. All right, again, that number of electrons before the big jump, all right, that one is equivalent to the number of valence electrons. And the number of valence electrons, that determines the group number of the element for the main group elements. All right, so we've already determined the number of electrons before the big jump, and that is 3. So the number of valence electrons is also 3. Therefore, this element with these given ionization energies here belongs to group 3. So the answer here is letter B. Metallic bonding is the strong electrostatic attraction between blank. All right, so what is metallic bonding? So metallic bonding is the strong electrostatic attraction between positive metal ions, or what we call cations, and the localized sea of electrons surrounding them. So the answer here should be letter C, between ions and the localized electrons. So in metals, atoms lose their outermost electrons, which become the localized electrons, and the remaining metal ions form a lattice, and the attraction between the positive ions and the localized electrons holds the structure together, giving metals their characteristic properties like malleability, conductivity, and high melting points. Thus, metallic bonding. The ionic radius of aluminum is smaller than that of nitride ion. This is because aluminum ion has, now let's dissect this one by one. So aluminum has 13 protons, and nitrogen from the nitride ion has 7 protons. All right, so this means that aluminum 3 plus aluminum ion exerts a stronger attractive force on its electrons than the nitride ion. And now let's take a look at the number of electrons. So for neutral aluminum, it has 13 electrons, and for neutral nitrogen, it has 7 electrons. But aluminum ion here loses 3 electrons, while the nitride ion gains 3 extra electrons. So that means originally the neutral aluminum has 13 electrons, and it loses 3 electrons, so that is minus 3 electrons. So it has a total of 10 electrons. This is for aluminum. But for nitrogen, it originally has 7 electrons for neutral nitrogen, and then it gains extra electrons because it has a negative charge. So we just add 3 electrons. So it has a total of 10 electrons too. So what is the effect of the charges of these ions? In aluminum ion, the high positive charge pulls the electrons very tightly, so it shrinks the ionic radius, while the nitride ion, the extra electrons increase electron-electron repulsion, expanding the ionic radius. Therefore, the ionic radius of aluminum ion is much smaller than that of the nitride or nitrogen ion, because the aluminum ion has a greater nuclear charge, attracting the same number of electrons more strongly, while nitride has weaker attraction and higher repulsion. So the answer here should be letter C. Aluminum ion has more protons. Okay, it has 13 protons, but the same number of electrons as that of the nitride or nitrogen ion or nitride ion. Which ion has the greatest polarizing power? Chloride, magnesium ion, sodium, or sulfide? So what is polarizing power of an ion? So a polarizing power of an ion, this is the ability of a cation to distort the electron cloud of an ion. So that means when in terms of charge, the higher the charge, the stronger the polarizing power. So higher the charge, higher charge, this means stronger polarizing power. And in terms of ionic radius, the smaller the radius, smaller radius indicates stronger polarizing power. Now let's take a look at the choices here, or the ions here, and then let's dissect them one by one or compare them. So let's start with chloride. All right, so chloride is a negatively charged ion, so this is an ion, and it has a large radius. Therefore, this is polarizable but not polarizing. So let's just say not polarizing. but polarizable. How about magnesium ion? So this one is a cation, okay, a positively charged ion. So this has a small radius with higher charge, high charge, positive to plus 2. So that means this has a very strong polarizing power, right? How about sodium ion? So the charge is plus 1, all right? Oh, but this one is larger, the radius for this is larger than that of magnesium ion. Therefore, this has a weaker polarizing power compared to Mg plus 2, magnesium ion. Right. And then we have sulfide. Right. So this is a negatively charged ion, an ion, and this has larger radius, and this is not polarizing but polarizable. Okay, so comparing these four ions, therefore the ion here with the greatest polarizing power is the magnesium ion. So the answer here is letter B. Which species is not tetrahedral? So we're given here four species. We have the carbon tetrachloride, we have the methane, and then tetraiodochloride. Oh, I meant tetrachloroiodide ion. So this one is iodine. So tetrachloroiodide ion, and then we have the ammonium ion. So let's check each species carefully. So we have here CCl4, carbon tetrachloride. It has four bonding pairs. If we're going to draw this pairs, but no lone pairs. So that means the shape of this is tetrahedral. And then methane, CH4. So this is the same as CCl4, has four bonding pairs, no lone pairs. So therefore, the shape of this is also tetrahedral. How about this tetrachloroiodide ion? This one. So the central iodine here has 7 valence electrons. 7 valence electrons. And then plus 4 from the negative charge. That would give us a total of 8 electrons. So bonding this one to 4 chlorine bonding to 4 chlorine atoms, then we use the 4 pairs, so leaving 2 lone pairs. So that would give us a total of 6 electron pairs in all, and that would the shape for that would not be a tetrahedral but a square planar, or maybe an octahedral electron geometry with 2 lone pairs. So it has 2 lone pairs, therefore this is not tetrahedral. And then for ammonium ion, NH4 plus, the nitrogen here forms 4 bonds and no lone pairs. Therefore, this one is tetrahedral. So among the choices here, only this tetrachloroiodide ion, or ICl4, which is not tetrahedral. Therefore, the answer here should be letter C. Members of the homologous series of alkanes have the same boiling temperature, density, empirical formula, or general formula. So what is this homologous series of alkanes? So members of the homologous series of alkanes have the same, right, general formula. And the general formula should be CnH2n plus 2. And they have the same functional group. They are all saturated hydrocarbons, carbon bond and carbon hydrogen, single bonds only. So saturated hydrocarbons. Okay, they have the same gradual change in physical properties, not appearance, physical properties like boiling point, density, viscosity as the molecular size increases, and they have similar chemical properties. All right, among the choices here, okay, we only have general formula. They have the same general formula. So the answer here should be letter D. An electrophile accepts a pair of electrons, always has a negative charge, always has a positive charge, or donates a pair of electrons. So what is an electrophile? All right. So an electrophile is a species that is electron pair accepting. So it is often positively charged or has a partially positive region. And this one is attracted to regions of high electron density, such as double bonds or lone pairs. So among the choices here, we have letter A, accepts a pair of electrons. So that should be the answer. So again, an electrophile is an electron pair acceptor and attracted to electrons. Calcium reacts with dilute nitric acid to form calcium nitrate and hydrogen, which is the balanced equation for this reaction. So it says here that calcium, which is a group 2 metal, reacting with dilute nitric acid. So there's a calcium plus nitric acid, and this forms calcium nitrate and hydrogen. So let's write the formulas for this. Calcium is Ca and nitric acid is HNO3, and then calcium nitrate, that is calcium nitrate NO3, and then plus hydrogen gas. So this one is an unbalanced chemical equation. So let's balance this. We have one calcium here, we have 2 hydrogens, so there should be 2 hydrogens here. And we have 2 nitrogens, 6 oxygens. So now this chemical equation is already balanced. And the one that is the same as that one is letter A. So the answer here should be letter A. What is the maximum volume of hydrogen formed at room temperature and pressure when 0.207 gram of lithium is added to excess water? And we're given here the chemical equation, balanced chemical equation. and the molar mass of lithium and molar volume of gas at room temperature and pressure, which is equal to 24 cubic decimeters per mole. All right, so we're asked here for the maximum volume of hydrogen formed, this one. And we're given the number of grams or mass of lithium. So we start with the given value, which is the mass of lithium, because we're also given here the molar mass of lithium. So we need to calculate for the number of moles of lithium first. We divide the mass of lithium, all right, by its molar mass, which is 6.9 grams per mole. So gram unit here cancels out, so we're left with the mole unit, and 0.207 divided by 6.9 is just equal to 0.03 mole of lithium. And now from the given equation here, let's take a look if it's really balanced. So we have 4 hydrogens, all right, oxygen 2, okay, it's balanced. So from the given equation, to lithium, the ratio of lithium to hydrogen is 2:1. So that is 2 moles of lithium is to 1 mole of hydrogen. All right, so 2 moles of lithium produce 1 mole of hydrogen. So now we can calculate for the number of moles of hydrogen from the number of moles of lithium that we just calculated. So moles of hydrogen, that is just equal to the moles of lithium times the molar ratio of lithium and hydrogen. So that is 1 mole lithium per 2 moles, no, 1 mole hydrogen. Okay, per 2 moles of lithium. Right, so this cancels out, so we're left with number of moles of hydrogen. So 0.03 divided by 2, so this is 0.0150 mole of hydrogen gas. All right, so we already have the number of moles of hydrogen here, and we are asked for the volume of hydrogen. And we're also given here the molar volume of gas at room temperature and pressure. So this is what we're going to do. We multiply the number of moles of hydrogen that we calculated by the molar volume of gas at room temperature and pressure. So, okay. So we will just multiply that 0.0150 mole hydrogen times the molar volume of the gas, hydrogen gas, which is 24.0 cubic decimeters per mole of hydrogen gas. So the number mole unit cancels out, then we get the volume, which is equal to 0.360 cubic decimeters. So this is the answer here, our answer. The answer here should be letter A. This one, letter A. So this one is the maximum volume of hydrogen gas formed at room temperature and pressure, given that mass of lithium that is added to excess water. What mass of anhydrous sodium carbonate is needed to make 50 cubic centimeters of a 0.08 mole per cubic decimeter solution of sodium carbonate? So we're given here the molar mass of carbon, oxygen, and sodium, and we are asked for the mass of sodium carbonate. All right. So the first thing we do here is we convert this one 50 cubic centimeters of 0.08 mole per cubic decimeter solution of sodium carbonate. We convert that to cubic decimeters, so we can get the number of moles of sodium carbonate required. So that is 50.0 cubic centimeters. So we just divide this by 1000. So 1 cubic decimeter per 1000 cubic centimeters. So that is 50 divided by 1000. That would give us 0.050 cubic decimeters. So this is now the volume of this solution in cubic decimeters. And now we solve for the moles, number of moles of sodium carbonate, right? But we're given here the concentration, so we just multiply the concentration and the volume. So that is 0.080 mole per cubic decimeters times this one, 0.050 cubic decimeters, and this unit cancels out. So we have 0.4 times 10 to the negative 3, or 0.0040 mole sodium carbonate. Okay, now that we already have the number of moles of sodium carbonate, so we can now calculate the mass of anhydrous sodium carbonate. So we need the molar mass of sodium carbonate first. So molar mass of sodium carbonate. So we have 2 moles of sodium there. So this is just 2 times 23. 23 is the molar mass of sodium, plus carbon, 12 times 1, plus oxygen, that is 3 times 16. So this is just equal to 106 grams per mole. And now we can calculate for the mass of sodium carbonate. We just multiply 106. So mass of sodium carbonate, this is just 106 grams per mole times 0.0040 mole sodium carbonate. The mole unit here cancels out, and 106 times 0.004 is just equal to 0.424 grams. So this is the mass of anhydrous sodium carbonate that is needed to make 50.0 cubic centimeters of a 0.08 mole per cubic decimeter solution of sodium carbonate. So the answer here is letter B. A sample of air with a mass of 5 kilograms contained carbon monoxide with a concentration of 12 parts per million by mass. What is the mass of carbon monoxide in this sample of air? So let's take a look at the given values here. So we're given a sample of air which is 5 kilograms, and it contains a carbon monoxide with 12 parts per million by mass. Alright, so those are the given values, and we are asked for the mass of carbon monoxide in the given sample of air. So take note here that parts per million by mass, this is just equal to parts per million, okay, parts per million, which is just equal to the milligram of solute per kilogram of sample. Or simply, or this is just equivalent to 1 gram per 10 to the 6 gram of sample. So 1 ppm is just equal to 1 gram per 10 to the 6 gram of sample. Oh, let's convert 5 kilograms to grams first. So we multiply that to 1,000. So the mass of air, given mass sample of air, is 5,000 grams. All right. So now we know the parts per million concentration value of the concentration of carbon monoxide. So we can get the fraction of carbon monoxide at 12 ppm of 12 parts per million. So that means 12 parts per million is just equal to 12 per 10 to the 6, which is just equal to 1.2 times 10 to the negative 5. And this is by mass fraction. All right. Now we can solve for the mass of carbon monoxide. So the mass of carbon monoxide is just equal to the mass of air times the mass fraction that we just calculated from the given 12 parts per million by mass of the concentration of carbon monoxide. So this is just equal to 5,000 grams times 1.2 times 10 to the negative 5. And this would give us a value that is equal to 0.060 gram, or just 6. We write this in scientific notation because we don't have this one in the choices given. So we write this in scientific notation as 6.0 times 10 to the negative 2 gram. So this is now the mass of carbon monoxide in the given sample of air. So the answer here should be letter A. What is the total number of structural isomers of the molecular formula C6H14? So this is hexane. Right? For hexane, we have the hexane or N-hexane. Then we have 2-methyl pentane or isohexane. Then we have 3-methyl pentane. Then we have 2,2-dimethyl butane, and we have 2,3-dimethyl butane. Right. Therefore, there are 5. The answer here should be letter B. There are 5 structural isomers of the molecular formula C6H14. So you can actually draw this using the simple dot and line sketches, or you can draw the skeletal formula for each one of these isomers.